Hello friend, in this video we will be learning time variant and time invariant system. In fact, we will follow a particular procedure to identify whether the given system is time variant or time invariant. Let us begin. Let us understand the definition first. If behavior of the system does not change with respect to time, then the system is said to be time invariant system. So as the name implied, it is something which is not varying with respect to time. That is, properties of a given system, if they are not varying or not changing with respect to time, the respective system is called as time invariant system. But on the opposite side, if there is a particular system whose parameters or whose properties are changing with respect to time, then the respective system is called as a time invariant system, right? So for example, let's say we have a time invariant system here, to which suppose you have applied this sort of input. So let's say you have applied some gate pulse here within the duration from 0 to 2. This is your x of t. And let's say you are getting y of t. So this is just an example where you are getting y of t here. So let's say for this particular x of t, let's say after applying this x of t, after processing on x of t, this system is producing this sort of output. For example, if same x of t is, let's say, delayed by some amount, let's say by 1, then it becomes x of t minus 1. Is that right? Therefore, what will happen? The above gate pulse gets delayed by 1 second. Then a new gate pulse I can draw like this, ranging from t equal to 1 to t equal to 3. Again, having same amplitude because I have operated only on time scale. Then it is expected output y of t should also get delayed by same amount. Then you must get y of t minus 1 according to time invariance property. Therefore, a similar triangle you will get, but then it will start with t equal to 1 and it will end at t equal to 3. Is that right? See, suppose to give you an example, suppose you are buying an amplifier. Then today if it is acting as an amplifier, after some days also it should act as an amplifier and it should amplify the signal with same amount of gain. And only then I will say that for that respective amplifier, gain of the system is not changing with respect to time. Whatever gain that you are having today, you will get same gain tomorrow, maybe day after tomorrow, or maybe after few months also, right? Because the property of that system is not varying with respect to time. Only the reason why I can say that a particular system is a time invariant system. Otherwise, if it is varying with respect to time, then the respective system would be called as a time variant system. For example, now in case number 1, I have applied this x of t, for which I am getting respective y of t, right? Same x of t you are not applying at the same time. Let's say you are applying tomorrow. That's the reason why in second case what I have done, I have delayed the same x of t by amount 1, right? Then you'll be getting same y of t not today but tomorrow, because you are applying this pulse tomorrow. So this triangle you are supposed to get tomorrow, it means it is getting delayed by the same seconds or same time. That's the whole idea of time invariant system. So this block diagram will make your concepts quite clear. Let's say this x of t is applied to a particular system. After processing on x of t, of course it is going to produce some output, let's say y of t. As you can see, there is a delay block, assuming it is delaying the input signal by t naught amount, and therefore if input is y of t, output would be y of t minus t naught, right? As you can see here, the same x of t is applied here. Now if you observe carefully, this delay block and system block are exchanging their positions. So instead of applying input to system first, it is applied to delay block first, and thereafter output of delay is given to the system. Therefore, let's say it is quite a similar delay block which delays the given input by t naught amount. So if input is x of t, I can say that after delaying it becomes x of t minus t naught. And let's say now it is applied to the system, assuming some output, that is y dash of t. If this y dash of t is equal to y of t minus t naught, it means if these two inputs after comparison we find that they are equal, then the respective system is called as a time invariant system. If y dash of t is not equal to y of t minus t naught, then the respective system is called as a time variant system. So whether it is time invariant or time variant system, it depends whether y dash of t is equal to y of t minus t naught or not, right? So what I've done, see once again, in first case x of t is applied to the system and thereafter it is delayed by t naught amount, output becomes y of t minus t naught. In second case, x of t is first of all delayed by t naught amount, so it becomes x of t minus t naught. So now input of system is not x of t but x of t minus t naught. Then we believe that output should be also y of t minus t naught, because that's the whole idea of time invariant system. So for any time invariant system, let's say if input is x of t, output is y of t, and if input is x of t minus t naught, then output should be y of t minus t naught only, right? So let's go through the steps to check the system whether it is time variant or time invariant. In first step, you have to replace t with t minus t naught and you have to get y of t minus t naught. It is because most of the time y of t is expressed as a function of x of t. So whenever you replace t with t naught, naturally this becomes y of t minus t naught. So whatever answer comes, it would be y of t minus t naught. And then we will name this equation as equation number 1. In second step, you have to delay your input by t naught amount. So for example, if previously input was x of t, then you have to make it x of t minus t naught. So you have to only delay the input and then you have to calculate output, and that output is what we call as y dash of t, for which you will be getting a particular equation. Let us assume this is equation number 2. And of course, what we have done in the block diagram in the previous slide, same we are doing it over here, right? Then we are going to check whether y dash of t and y of t minus t naught are equal to each other. If yes, then the system is time invariant, else it is time variant system. So if we start with the numericals, then it would be quite clear to you. Question says, check whether the following systems are time invariant or time variant. The first question says, y of t is equal to x of 2t. So we will be following the steps. Step number 1 says, replace t with t minus t naught. So wherever you see t, just replace t with t minus t naught. Therefore, on left hand side it will become y of t minus t naught, and now it is equal to x of 2. In the bracket I will have t minus t naught. So if you open the bracket, y of t minus t naught is equal to x of 2t minus 2t naught, and now it is equation number 1 for us, right? Let's go for step number 2. In step number 2, remember you have to only delay input by t naught. Therefore, output becomes now y dash of t. It is equal to x of. In the argument, what is written, see carefully, it is 2t, then you have to delay it by t naught. So it is 2t minus t naught. So now it becomes equation number 2. Remember, whatever argument is written over here, just subtract minus t naught from the given argument, and that becomes y dash of t. And now if you observe equation number 1 and equation number 2, you can see clearly that y dash of t is not equal to y of t minus t naught. We know that if equal condition is present, it is time invariant system, else it is time variant system. So now the given system is time variant system. Therefore, it is time variant system. So in future, if you don't have to follow these many steps, then you can remember some shortcuts. See to it what is done with the argument of x of t. Original signal is x of t, but what is written y of t in terms of x of t as x of 2t. So what is done exactly? It is nothing but time scaling. Remember, time scaling on the argument of x of t makes system time variant. So you can just see, whenever a time scaling is taking place on the argument of x of t, you just make sure that system is always time variant system, right? So in future, if you just observe this, you can write the direct answer instead of following so many steps. Let's start with the next one. Now it is y of t is equal to x of minus t. Let us see by following the number of steps to check whether the given system is time variant or time invariant. Step number 1 is to replace t with t minus t naught. So it gives you y of t minus t naught, that is equal to x of, now we have a negative sign, so t has to be replaced with t minus t naught. Let us simplify this. Y of t minus t naught, finally I can write x of minus t plus t naught, right? Now it becomes equation number 1 for us. In step number 2, you know that you have to delay input by t naught, and you know very well, whatever present in the argument of x of t, just subtract t naught from it. Therefore it gives you y dash of t, which is equal to x of minus t naught, and now it is equation number 2. Observe carefully, equation number 1 and equation number 2 are again not same. Y dash of t is again not equal to y of t minus t naught, and it says that the given system is a time variant system. Y of t is equal to x of minus t, where x of minus t is what we called as a time reversal property. Am I right? In fact, a time reversal property is a special case of time scaling only, because for time scaling what we write is x of alpha t. Instead of x of alpha t, if I now substitute alpha equal to minus 1, it ultimately becomes x of minus t, right? And as we have already studied, whenever a scaling takes place on the argument of x of t, it always gives you a time variant system. Therefore it is a time variant system. With respect to input variable x of t, if scaling is done, it always gives you time variant system. Now y of t is equal to x of t minus 2, right? Let us follow the steps. Step number 1, replace t with t minus t naught. So it gives you y of t minus t naught, which is equal to x of t minus t naught minus 2. So it becomes equation number 1. In step 2, we just delay input by t naught, right? Therefore it gives you y dash of t now. So what we do, we keep the argument same, we just subtract minus t naught from it. I can rearrange like this, x of t minus t naught I can write together, and thereafter I can write minus 2 also. The reason why I'm writing like this, so as to match with equation number 1. You can see clearly now equation number 1 and equation number 2 are exactly same. So I can conclude y dash of t is equal to y of t minus t naught. And whenever y dash of t is equal to y of t minus t naught, so it is a time invariant system. Now if you observe what is done with variable t with respect to x, it is nothing but time shifting. So now you can conclude that time shifting, when you say time shifting, it can be delay or it can be advance also. It keeps your system as time invariant system. Let us summarize what we have studied. For a particular system, when y of t is expressed in terms of its input, that is x of t, in any form, with respect to x of t variable, that is t variable, if time scaling is done or time reversal is done, then definitely it is time variant system. But in case if time shifting is present, whether it is delay or advance, then it remains as time invariant system. So now if you look at this sum, if only by observation if I want to know whether the system is time variant or invariant, then. So this is actually an integrator system, right? So it is a system where x of t is input and y of t is output. So y of t is given as integration from minus infinity to t x of tau d tau, right? So this is a perfect integrator system. So in this integrator system, you have to see variable t which is related to input. If you see t, neither time shifting is done or time scaling is done. Therefore, it is 100% time invariant system. But let us prove it by following a standard procedure. So in advance, I know that it is time invariant system for sure. Step number 1, replace t with t minus t naught. So it becomes y of t minus t naught, which is equal to minus infinity to t minus t naught x of tau d tau. So it becomes equation number 1. Step number 2, delay input by t naught. So it gives you y dash of t. Lower limit and upper limit are not going to change because you don't have to really replace t with t minus t naught. You have to only delay input by t naught. So you know that what we used to do will be following the same. You have to only check what is argument of x and just subtract minus t naught from the given argument content. So it becomes x of tau minus t naught d tau. Is that right? And now it becomes equation number 2. If you observe equation number 1 and 2, it gives you a feel that definitely these two equations are not same, and one might make a mistake to conclude as it is a time variant system. But let me tell you, it is a time invariant system and I'll prove it. So how we are going to prove this? The reason why they are not seems to be equal, because what we have in argument over here is tau and what we have over here is tau minus t naught. Let us assume we are replacing tau minus t naught with p. Replacing tau minus t naught equal to p. So when I say tau minus t naught equal to p, then I can say that d tau equal to dp, because t naught is constant, therefore derivative of t naught would be 0 only. So d naught, so d tau equal to dp. Now you know that you are going to replace this with p, okay? So d tau will become dp, right? But then you will have to check lower limit and upper limit also. So let us go for lower limit calculation. In lower limit, it was with respect to tau, so tau was equal to minus infinity, right? And what we have relation as tau minus t naught equal to p. Replace tau with minus infinity, so minus infinity minus t naught, that is p. Therefore p will remain minus infinity only. So lower limit remains minus infinity. Let us check upper limit. So upper limit was simply t, so tau was equal to t, right? But now we have a new relation, that is tau minus t naught equal to p. Replacing tau value equal to t here, so t minus t naught becomes p. So new value of p is t minus t naught. So now this becomes lower limit and this becomes higher limit. Okay. Now we are going to change our equation of y dash of t. So y dash of t is equal to, what is the lower limit? Lower limit is minus infinity. And what is the upper limit? Upper limit is t minus t naught x of, what we had over here is tau minus t naught, which is replaced with p, and instead of d tau we have dp, right? Now if you see carefully, you have to make this as equation number 3 and compare equation number 3 with 1. Equation 3 and equation 1 are exactly same. Now it may differ that what you find over here is tau and what you find over here is p. So let me tell you, whether it is tau or whether it is p, it is just a dummy variable. So dummy variable can be anything, right? But if you see, ultimately lower limit and higher limit are exactly same, with tau as a dummy variable in equation 1 and p as a dummy variable in equation 3. It really doesn't matter. Therefore I can say that equation number 1 and equation number 3 are exactly same, that is y dash of t is equal to y of t minus t naught. Therefore the given system is time invariant system. But if you really don't have to go through a huge procedure, then you have to really remember certain tricks, and those tricks are you have to always check variable t with respect to input, right? So here neither scaling is done nor shifting is done, and let me tell you, shifting really doesn't matter, because only if shifting is done it remains time invariant system only. This is what we have already seen with an example, right? So let's see the next example. Example says y of t is equal to integration from lower limit as minus infinity, upper limit is t minus t naught x of tau d tau, right? And if you recall the previous equation, it was like this: y of t is equal to integration from minus infinity to t x of tau d tau. The reason why I have declared this was time invariant system, reason, by observing this upper limit t, right? Now you can observe upper limit is t minus t naught. So what is done with t variable? It is just a normal shifting. It is just delayed with t naught, and you know that shifting doesn't matter. In fact, it remains time invariant system only. Again, we are not going to follow that huge procedure. In fact, I am going to declare over here it is a time invariant system. For example, let's say if y of t is equal to lower limit is minus infinity, upper limit is, let's say, 2t x of tau d tau. What do you think? The system is a time variant system or time invariant system? We always check variable t with respect to input. Only here I see a presence of t, and that too scaled with 2. Definitely, if time scaling is done, it is no more time invariant now. It becomes time variant system. So as I said, only by observing you can see whether it is time variant or time invariant system. So this is what you should know from gate point of view, because if these tricks are not known to you, you will go through that huge procedure. I don't say that you won't be getting answer, but yes, you will be losing a time, and time is money.